On our robot, we have two big motors directly attached to the EV3 brick for a low center of gravity. We also make use of a gyro sensor that makes our turns perfect and also tests our turns if it was correct. And at the front here, we have one small motor, and at the back we also have a small motor, and they work perpendicular to one another. On our bottom here, we have two color sensors so that we can make incremental adjustments against each line, and also for dual line-align programming. And at the back here, we also make use of a color sensor.
On our two small motors at the front and the back, power transfer is created. On the front motor, we have two small wheels without rubbers on them. Then when our attachments go onto the robot, these two wheels have axles sticking out of them. As they slide over the robot, these axles fit into the holes on the small motor and power transfer is created. On the side, we have bubble gears, and these bubble gears doesn't have a great mesh, so it's easy to fit them into one another. We made use of several My blocks, all fitted into a menu structure. The menu structure allows us to automatically select the program with the color piece of Lego over the third color sensor. As the attachment go over the robot, the color sensor will be covered with a piece of colored Lego, and we only have to push the middle button. This automatically selects the correct program, as well as this minimizes the chance of selecting a wrong program. We also made use of some reusable code where we wrote My blocks, which we can use over and over again. The first My block is a distance My block. This block allows us to enter the amount of centimeters we want to drive forward and in what power, and the robot automatically converts this to rotations. We have one for our dual align program, where the two color sensors in front drive up to a line, and if it comes in skew, it automatically corrects itself incrementally against the line. Then we also made use of fail-safe programming. What this does, it resets the motor's encoder value on a specific place on the playing field. As the robot drives forward, searching for a line, for example the red line, and due to varying light values, the robot might miss the red line, the motor's encoder value will exceed a specific limit, and it will tell the robot to exit the loop and continue with the rest of the program.
We developed our strategy keeping in mind the amounts of points we could score in the allotted time. We have something to consider in terms of the engagement multiplier, which brings up your score as you go along. We decided to go for a high score and a low engagement multiplier score, rather than a low score and try and achieve a high engagement multiplier score. So what we did was we designed our runs or our mission model doing in such a way that we save time by deciding to sacrifice a loop from some of the mission models and retrieve the robot so that we can score higher. For example, we score 400 points and multiply with 10%, then you get 440 points. Or you can go and score low and multiply with 20%. Say you score 200 and multiply with 20%, then you get 240 points.
Now we'll demonstrate one of our runs for you.
The robot will drive up to the red line. It will turn using the gyro sensor. We align incrementally against the green line. We turn using the gyro sensor. We align against the black line. We score a goal using elastics. We insert the insert and catch the loop. We turn using the gyro sensor. Use cantilever action to drop the arm. We turn using the gyro sensor and we collect the loop. Some special features on our robot would be our unique power transfer, as well as our fail-safe programming, where we use the encoder values to measure if we missed a line or not. We also make use of fail-safe programming where we program in seconds instead of rotations. If the robot snags or gets stuck onto a mission model or has to drive into a wall, it will be stuck until the specific amount of time has elapsed, and it will continue with the rest of the program.
and some unique features on the attachments. We use elastic bands to shoot the ball to the goal, and we use a cantilever action to insert the insert, and we use a lot of 90 degree power transfers to let our lever fall out.
We made extensive use of gravity in some of our attachments. We use a slider mechanism. As the robot drives into the wall, this slider mechanism moves back and allows the loop that has to hang on the project-based learning. It allows them to fall down and hook onto the scale over here.
We also made use of a dual flexi arm to do the adapting to changing conditions, and universal joints to transfer power at an odd angle. And in this attachment we used gravity, so when this is pushed it only falls out and we can leave it behind.
During the season, each of us on the team had a role. For example, I started with strategizing in the beginning of the season.
I had to make sure that before every run the field was completely and correctly set up.
I pampered Inspire One and washed its wheels.
I made sure the playing field was clean every time we practiced.
I was head programmer.
Me and Luca was head builders in building the attachments and the robot.
The most unique feature about a robot would be the fail-safe programming, which allows us to navigate properly and effectively even in light conditions that aren't satisfactory. So if we miss a line, we will be able to function without that sensor feedback.
And we use a gyro that not a lot of teams use to turn correctly and see if we actually turn correct. And our unique power transfer is achieved by using the small wheels in front and the bubble gears at the back. Our most difficult mission was the long run, because there's a lot of places where our robot needs to detect the lines, and the small thin line it must detect is hard to detect because it's very small, and there's a lot of stuff that can go wrong if the robot doesn't align correctly.
But we overcame that with our fail-safe programming.
We are now busy developing new attachments in order to score more points on our board. Charles and Ulrich will demonstrate and explain these new attachments.
On this attachment, we combined two attachments into one mission to save time and score higher points. In this run, we have these wheels that drive against the wall, as well as this arm that falls out to collect the correct loop. In this run, we drive against the wall for accuracy. We use the same slider mechanism to release the loop and insert the people into the circle, and then we calibrated the gear ratio in such a way that we can turn the search engine very slowly and calculate at which position the correct loop will be, so we can save time in collecting the loop in one run.
We wanted to do the multiplier to get more points on the board, so we push out the attachment, and when you drive back it doesn't hook on the attachment because we added wheels so that it can drive smoothly over it. And we found a loophole that you can leave it there and take the junk penalty, and then you can still use it and it isn't against the rules.
We struggled to get power toward the multiplier efficiently, and the idea behind this is a clock that uses wound up energy and stores it to use it at a later time. To store some of our energy, we use pneumatics to push this weight over the side of the table. And then we thought of an idea to control this energy. We thought of a pendulum that a clock uses, and this axle creates the effect of a pendulum. As we touch this lever, we release the weight to spin a full 180 degrees and turn the multiplier.
With our ticker, we designed this it has a lot of 90-degree power transfer to turn our wheel in front. So we just need to turn it at 90 degrees and it will tick the lever just once, so that the ticker is turned 180 degrees. So every time it's ticked, it runs.